All right, there we go. I am very pleased to introduce Professor Kirk Kolenbrander. I hope you all read the biography that we sent out yesterday, but I would like to add to that. I've known Kirk for many, many years. We both go to the same church. Our daughters grew up together. But one thing that really impressed me most recently, as we were talking about the fact that he teaches in Chemistry 101 course, right? Which is one of the mandatory courses that you have to take if you go here to MIT, that he is one of the many professors that asks for student reflections. As part of the learning process, he's asking his students to reflect on what they've learned every week and to provide guidance and feedback on his lectures. And Kirk reported that he read and answered every one. That was an amazing feat for me. I've done that for courses, design courses, where I had 20 students and found it difficult to do. So I thought it was amazing, and I think you're going to be very impressed with his talk today, right?
We'll see. We'll see.
So let's welcome Kirk Kolenbrander.
Thank you. Thank you to all of you. That's very kind of you. I thank you. I thank all of you online who I can't see, but I know you're there. I'm really delighted to be here today for a couple of reasons. One is that I find this topic, the topic of how is it that we address the big, bold challenges that are in front of us as a society, and the communities of which we're a part. How do we listen to those communities as they tell us what the problems are that need our solutions as engineers and scientists? And then how do we take that information and turn that into solutions, into game-changing ideas? And so I want to talk about that process with all of you, and I want to share a bit of some of that work that's going on at MIT and elsewhere along those lines. But the second reason I'm delighted to be here is because I've been at MIT so long. I've been at MIT for 35 years. I've been on the faculty. I've been a part of the senior administration in a bunch of different roles. Now I teach full-time. But I know for a fact that MIT can only be the institution that it needs to be for the nation and the world when it can attract the very finest young people. And that's all of you, right? You are, in fact, MIT right now, and hopefully some of you will be MIT a year from now or 2 years from now as you apply and then go through the challenging but important admission process. So it would thrill me to know that 14 months from now, a bunch of you are sitting in my classroom, this 3091, Joel called it Chemistry 101. 3091 Introduction to Solid State Chemistry is a class of about 600 students. We meet Monday, Wednesday, Friday at 11 a.m. and you have to put up with me. And we talk about solid state chemistry. And we talk about how MIT turns big problems into bold ideas in the context of the development of new materials. And that's what we're going to talk about. So in that spirit, the reason why I put this talk in this context is because there is a shared purpose here at MIT, and I think you sense it by being here, and those of you online, by being a part of the community. MIT aspires to make game-changing contributions to solving some of humanity's great challenges. Lots of universities will talk about that, but MIT lives it out every day. That whether we're talking about the most distinguished professor or our students, our graduate students, our undergraduates, or we're talking about the custodians who sweep the floor, we're talking about people who are committed to this notion that MIT wants to be making game-changing contributions to not just advancing science and technology, but to advancing science and technology to those problems that the society has said, hey, we really need help. And so you've seen that play out and the role that MIT plays in that. Certainly World War II and MIT Lincoln Laboratory played a huge role in the development of convenient radar systems. And it's no exaggeration to say that radar played a massive role in the Allies winning World War II. And I can show you the buildings at MIT where that was developed. Or we can talk about guidance systems for the Apollo moon rockets, where that came out of MIT. Or we can talk about cancer research and the fundamental cell-based techniques that are still used today that MIT professor Salvador Luria won the Nobel Prize for developing. It's sort of the DNA of the place, that we're looking at these fundamental problems facing society and we're saying, what is it that we can do? And so my first stop in this journey that we're on together is to ask you, well, what are those great challenges today? So my generation, Joel's generation, we're contemporaries, have done a lot to mess up this planet. And it's up to you to fix these missteps, these errors, for the planet, for our communities, for our society. So if we're going to just start and say that MIT aspires to make game-changing contributions to solving some of humanity's great challenges, well, what are they? What are the great challenges facing the world that you are moving into right now as adults? I'll take hands. Yeah. Yes, you.
Climate change?
Climate change, excellent, of course. It's everywhere, yes. Famine, food security. And can we put water security in there too? If you travel the world and talk to world leadership, oftentimes they will tell you the number one problem they're facing is clean water. How do we get enough water into people's hands that they can survive and support commerce? Yeah.
There's also wars.
Okay, political infighting. What else?
Access to reliable healthcare.
I'm sorry, reliable
Healthcare.
healthcare. Thank you. Disease, medicine. What else?
The digital divide.
I'm sorry?
Digital divide.
Okay, access to information, right? What else?
Demographics,
Okay, tell me about that.
like I guess there's some countries have like a low fertility rate, and then they're like they're not having a lot of young population, so they're like having impacts on the workforce in the future.
Good. Let's take two more. Yes.
Pollution,
Pollution tell me what kind of pollution you're thinking about.
like trash in the seas or air pollution from factories.
Good. And right behind you.
Women's rights.
Okay. Good. Very good. All right. Indeed. All of those and more, right? I've just put a bunch on the screen: clean water, food, climate change, energy, housing, sustainability. These are all fundamental issues. What fuels a class like my Introduction to Solid-State Chemistry to 600 students, that will include many of you, I hope, in 14 months, is to what extent do materials stand at the intersection of our ability to make the big game-changing solutions? To what extent do we actually have to build new things, new materials that allow us to make those changes? And indeed, I want to, if there is a common thread here, it is that that new materials often are what allow these game-changing solutions to take place. So to give you a sense, let's just imagine if the game that I'm constructing for us is that we need to design new materials to allow us to make these changes to these problems that you described. Well, what do they have to do? Well, you know, you're living it right now. Joel was telling me there's a textile group in purple, right? Talk about materials. Right, these are these are classic materials in our society, right? And so how do we think about what materials like that need to do? All 6 groups, I'm sure we can find, 6 groups? 6 groups. We can find materials at the core to solving the problems you're working on right now. So what are our new materials going to have to do? Well, if we're dealing with water security, filtration, adsorption, these are going to be fundamental challenges. Energy storage. Wow, energy storage. So here's the deal. In 20 minutes time, the sun delivers as much energy to the planet every 20 minutes as is contained in all of the fossil fuels that have ever existed on this planet. In 20 minutes. Every 20 minutes, the sun is delivering massive doses of high-quality energy to the planet. Yay, but the sun doesn't always shine. So if we're going to use that sun to give us the energy we need in whatever we're doing, somebody better develop some very sophisticated energy storage systems. Well, good news, I put my iPhone in my backpack so it's not, but solved problem, right? We've got lithium cells everywhere. Yeah, well, we'll talk about some of the problems with that technology and how it is that we can work through that. But storage, sensing, protection, transformation, these are all qualities of the materials that we're going to have to develop. But you've heard me make a change here. I'm not talking about MIT anymore. I'm talking about you. Right? MIT isn't. MIT is a bunch of concrete blocks or whatever it is that we're sitting in. Right? MIT isn't going to solve any problems. It's you. And I try to challenge who do you think, where do you think those students were who solved some of the problems that we started this talk by talking about? They were sitting right where you're sitting now, right? They're you 40 years ago or 50 years ago or 20 years ago or 5 years ago. This is what they look like. And so it's you who was going to, throughout the rest of your careers, turn these problems into bold ideas. So I want to show you several different examples, and we'll talk about them. So the first one I talked about, I already mentioned, energy storage. Can we make them safer, faster, and more energy dense, right? So energy storage is a solved problem. Energy storage was a solved problem when I was a little boy. We had flashlight cells, D cells, so we knew how to store energy, but you're not going to drive a car at 65 miles an hour down the Massachusetts Turnpike on a D cell, right? So you all have grown up in a world that understands much more energy dense, safer, faster systems, but we're a long way away from where we need to be. And you know that if you've been on an airplane recently, you know that as part of the safety instructions the flight attendant gives you, they say if you happen to drop your phone in between the seats on which you're sitting, don't do anything but call the flight attendant. Right? What are they warning you to do? They don't want you to move your seat. Why not? Because you might puncture the phone. And if you puncture the phone, do you know what happens? It burns up. And why does it burn up? Because it has an enormous amount of energy and a very flammable electrolyte. And that kind of fire is extremely dangerous on an airplane. And so the flight attendant would much rather be troubled by you and having them fish that phone out by the seat next to you, rather than you try to do it and then fail. So how would we build not a polymer-based lithium-ion battery, which is what we have today? So how does a lithium-ion battery work? Well, you've got these lithium ions that are moving back and forth between the cathode and the anode, anode is where oxidation takes place. And so you see the lithium transiting that separator. If you could build it out of a solid instead of out of a polymer, you would be able to address the flammability, but you'd also be able to solve a couple of other big problems. One is recharge time. I have Iowa roots. Terry and I grew up in Iowa and love to drive to Iowa. We use gasoline cars because I'm not ready yet to pull up to the charging station and wait the 25 minutes, 30, I'm not a patient person. 35 minutes, whatever it takes to recharge the cells in the car as we make these long trips. And so recharge time makes a big difference. Energy density, of course, is obvious that it's always a better thing. This dendrite formation, that's dendrites, those are the things that stick across the electrode or across the separator and short out the battery and lead to catastrophic failure, right? Dendrites are real, and dendrites have to be controlled or the battery blows up. You need to understand how dangerous these things are that are in your pockets, right? They're massive amounts of stored energy sitting in your pocket, and you take it for granted that there's something in there that keeps that energy separate from combining explosively. Well, that's the separator. So, but let's build that out of a solid electrolyte. And so here's one, lithium lanthanum zirconium oxide, LLZO. Material scientists love crystal diagrams. And so you see here the unit cell of LLZO. Take a minute to decode it. There's inside those boxes, if you will, are gray spheres. That's the lanthanum. The pink, green, and yellow spheres, those are lithium atoms in different locations. And the red, that's the oxygen. And so if you stare at that long enough, you can start to see a channel setting up where that lithium moves through the channel. This is key, right? You're building an ionic conductor. You're building an ionic conductor. You want to move the lithium quickly, reversibly through the channel. Channel is your friend. How would you make it faster? You want it to be faster. What's the first thing you're going to do from a materials design problem? How are you going to make that system faster to lithium transit? Yeah.
Increase the width of the channel.
Thank you. You're going to make the pore bigger. Of course that's what you're going to do. Thank you. Exactly. So how would you do that?
Smaller atoms.
Okay. So the lithium, so one way to do it is to make the lithium smaller. Is that a good plan? What do you know about lithium on the periodic table?
It's reactive.
It's very reactive. It's explosively reactive, thank you, but where is it in terms of size? It's 3. It's number 3. It's teensy. So if the game plan is let's make lithium smaller, good luck to you. Right? Okay, so what's the converse of that? Make the pore bigger. How are you going to do that?
Increase the crystalline.
Thank you. You're going to replace the lanthanum with something bigger, right? So here you see research going on a few years ago. We're going to substitute zirconium 4+ for cerium 4+. Cerium is a rare earth, but it happens to be the most abundant rare earth, so there's really quite a lot of it. And you see in the triangle dead center in the bottom, we make the pore bigger. Come on, we figured it out right here, right? We figured it out. You knew. right? So now it's just a matter of building that new material. So you might say, well, what, can I go to Amazon and buy this? Well, of course not. I mean, these are very sophisticated materials. Nobody's ever built that material before. And so, but you're going to, because you know how. You're probably going to use artificial intelligence to help you design that system, right? I said cerium, but why might you not choose a different rare earth? You might, right? And so you want to think about all that. But that's a really nice example of using just good, thoughtful common sense to solve a really important problem. Let's go to the next one. Disease detection. We had disease, right? Good. So gastric cancer kills people. Why does it kill people? Because it's hard to detect, right? By the time anybody knows it's there, things have run away. We have lots of information on cancers. I just had a biopsy right here of something growing on my forearm. We can see that, and the biopsy comes, it turns out it's just something, I don't know. When you have red hair, I used to have red hair, you have that, but it's fine, everything's fine, but those kinds of cancers are easy to see. What about the cancers that are deep inside of us and don't have an image? How can we improve our disease detection? This is a micrograph. Material scientists love their microscopes. So you're seeing here the surface of a germanium phosphide monolayer. Germanium is a group 4 semiconductor that sits below silicon. So it's carbon, silicon, germanium. Do you ever wonder why they make you learn that stupid periodic table? This is why, right? Because you're going to be in the business of building out new materials. So you need to know how these things are related. Carbon, silicon, germanium. Germanium phosphide is a 4-5 semiconductor. That's quite uncommon, but it's easily available in monolayers. So what you're looking at here is the electron micrograph of rows of atoms, because this is what atoms do in crystals, right? They actually form these perfect rows. And you're saying, Kirk, apparently your old age has affected your vision. There's nothing perfect about those monolayers. You see all kinds of defects, right? What you're seeing there are point defects, or you're seeing vacancies, vacancy defects where the atoms are missing. Defect is a pejorative word in that it sounds bad. Here, defect is good, because what we're going to do is we're going to put that very material inside your gastric lining, inside your stomach, along with some gold nanoparticles. Now, it turns out that gold nanoparticles have a particular affinity to the microRNA that is associated with gastric cancer. So we know what the RNA signature is for gastric cancer. So in that sense, good news, we know what to look for. The problem is we can't get nearly enough of it to detect it. So we have to increase the concentration. We have to increase the concentration. And so what we're going to do with this defect ridden germanium phosphide surface is in the stomach, we're going to let these gold nanoparticles settle onto those defects where they are particularly happy and particularly stable. And they will collect there on those defects, and we'll go in and pull out the thin film of germanium phosphide and just do a certain spectroscopy on it using a light source and a detector. And we will detect, because we now have the concentration that we need, the presence of that gastric cancer. So here is a new material being applied to detection of a nasty disease. And I happen to choose this one, but we could have chosen any number of different pathways that allow us to understand what's going on. Parkinson's, as an example, we know Parkinson's has a lot to do with errors in protein folding. So if we understand how proteins fold, then we can get a handle on how to keep them from folding in the wrong ways and get a handle on Parkinson's disease, for example. So these are exactly the kinds of things that engineering and science allow us to take hold of these kinds of problems. One more, third, feeding the world. Food security. Here's a graph of the world population over some 420 years. And no real surprises here, except that's a hockey stick, right? Something happened. Something happened right around here. The reason why this growth occurs is because we didn't have the ability to feed any more people than that. And so that's what was limiting the global population until now, until this point right here. What happened? What is it? Okay, GMOs. So Norman Borlaug develops hybrid crops. What else? Thank you. Fertilizer, right? Both of those are true. Both of those happen in roughly the same time period. The development of ammonia-based fertilizers and hybridization, GMOs, that allow us to, be careful, explosions occur. Indeed. And so it's the Haber-Bosch process that creates ammonia in large quantities for the first time. And that happened in about 1920. And so let's look at the Haber-Bosch process. It's beautiful chemistry. All we're going to do is simple. All we're going to do is take nitrogen, N2, and hydrogen, 3H2, and combine it to form ammonia. Great. It turns out that from a commercial, industrial perspective, solved problem. Solved problem. We know how to make ammonia by the train car full, or the, I don't know if we ship ammonia, probably. So we can make tons and tons and tons of ammonia today. It turns out there are two problems, though, with today's technology. You saw one of them in the last 2 months. Fertilizer prices have spiked because methane prices have spiked. And methane prices have spiked because the Strait of Hormuz is closed. And so all of a sudden, there's talk of famine. There's talk of famine right now because we can't feed the world because we rely on these ammonia-based, and they come from methane, of all things. Methane is CH4. Now you might say to yourself, CH4, that doesn't sound like ammonia. So one of the things we need, it turns out, is methane. Why? Because in that formula of N2 plus 3H2, is nitrogen abundant? Is hydrogen abundant? Not in these quantities. So the way we make hydrogen today is called reforming of methane and water. We take methane and oxidize the carbon of methane in the presence of water, and that liberates H2. We get lots of H2. Hand? You can. We'll get to that. Absolutely. But the way we do it today is we create the hydrogen that way. But the problem is, one, now you're relying on fossil fuels, which of course our entire society relies on fossil fuels, so that's not new. But the second thing is you're making CO2. So when the methane combines with the water, the products are hydrogen and lots of CO2. And that has massive environmental consequences, climate change. So we need to get out of the burning methane business if we're going to make green hydrogen, clean hydrogen. right? So in fact, we can use an electrolyzer. We can take wind power, solar power, and use that electricity to separate the hydrogen and the oxygen, store the hydrogen, and then use that hydrogen, combine it with nitrogen in the Born-Haber process, and off we go. But what if we flipped the whole thing around? What if we never went through hydrogen? That changed the whole supply side thing. This is research going on at MIT right now in fact, material science and engineering. What if we use the Earth itself, the rocks, to serve as a reactant bed for nitrate-filled water? This is water coming in. That's going to end up being our source of hydrogen. And the nitrate is the source of ammonia, and out comes NH3. We're trying, if we could actually do this at quantity, it changes the game completely. What's the new material here? Well, actually, there isn't one. It's the Earth itself. It's the Earth beneath our feet that would serve as the material that drives this chemical reaction. That's pretty cool. And so, maybe not while you're a college student, but maybe when your children are running around, they're going to be thinking that this is where ammonia comes from. It comes from the Earth. It comes from these whereas we think of it as, of all the crazy things to do, we burn methane in order to get ammonia. But we do it because it works so well. It's just that it generates a lot of CO2. Okay. Finally, one last topic, sustainability and a role for you. So that's Professor Yet-Ming Chang. He is a professor in material science and engineering at MIT. This was a story that showed up a couple years ago in Forbes, Forbes being a financial periodical. Meet the MIT professor with 8 climate startups and $2.5 billion in funding. So $2.5 billion is a lot of money. They say that Taylor Swift's Eras tour generated something like $1.5 billion in global revenue, okay? Which is a lot, but that's 1.5 Taylor Swifts, right? That is a ton of financial interest in sustainability. What does that mean for you? Well, one thing it means is jobs, right? That money goes to employ people. So there are jobs to be had, but let's just move on. These are, in fact, companies that have spun out of Professor Chang's lab. A123 was a big battery company. American Superconductor. These are all different companies that, so as you know, MIT has a very entrepreneurial spirit. Professor Chang has a very entrepreneurial spirit. I want to tell you about this company, Rock Zero, because it gives me a chance to tell you about this student, Jacqueline Prawira. Jacqueline just graduated. She just graduated in May. But I don't want to tell you about Jacqueline as a senior. I want to tell you about her as a first-year student. This is her in the lab, standing next to a postdoc. And they're working on spodumene, which is this unit cell. It's essential to lithium extraction. So if you wonder where lithium comes from that goes into your lithium batteries, it often comes from the earth in the form of spodumene, and it's also, that material is also very important in concrete manufacturing. Anyway, you don't really care about that, but what you might care about is this patent that was issued to Professor Yet-Ming Chang. That's the $2.5 billion guy. There's Jacqueline, the third name on the list, Camden and Benjamin. I think that's Camden in the photo. What do you need to know? 4 people are listed on this patent that was issued in August of 24. 4 people. First name, world-famous professor. Name 2, name 4, experienced PhDs. Jacqueline, freshman. That's what you need to know. How cool is that? Right? Freshman. Yeah. That's MIT. I love to tell this story because at MIT, it doesn't matter who you are. If you've got ideas, bring them to the table, right? And so there you see her carrying out her ideas that leads to a patent, that leads to, that's the intellectual backbone to Rock Zero, which is now a heavily funded startup that, believe it or not, Jacqueline works for as a summer intern. So it's her intellectual property that is driving the company that pays her this summer before she starts as a graduate student this fall. So Jacqueline is continuing on in her studies. The future is designed by those who make new possibilities real. Who better than you? And so that's where I want to end. Who better than you? I very much hope that you have a great experience this summer. I know you will. But I really hope that you decide you want to apply to MIT. And I really hope that I see you in class in about 14 months. Or for those of you who are rising seniors, what is that, 26 months. I look forward to that. I look forward to having you in my classroom where we can start to pursue some of these ideas further. So with that,
We're going to start with the 2 online questions
Great.
first. Stop the screen share so we can see our virtual students.
great. Thank you.
Jessica, do you want to pick someone?
All right, Niropama, can you unmute and ask your question?
Hi, thank you so much for speaking to us. I really enjoyed your seminar. I thought it was really interesting.
Thank you.
So you discussed several examples where the material science is being used to address major challenges in society, from like energy storage, disease detection, food security. So how do you decide which problems are best approached through material science, and what makes you believe that a particular materials-based solution has the potential to create a meaningful change?
Yeah, great. So how do I decide? Really, it is impossible. It's almost impossible to not find a materials angle to almost any problem. There are issues of pure politics or religion and politics, right? Materials are going to have a hard time there. But they might actually be useful in how information is shared or in creating opportunities for dialogue, but that's a little subtle. But in general, the sort of the thesis of this talk is you can't hide from the materials problems. They're there. And you're living them right now. This is, tell me if there's a group here that's working on a problem, or a group online that's working on a problem, and that you can say confidently, materials has nothing to do with it, let me know. Tell me now. And the reason is because you've got to make it out of something. And that something is probably limiting what you can do with it, right? So if you could make it out of something different, right? Don't limit. So what's Kirk saying? He's saying don't limit yourselves to the stuff that you can find at Amazon, right? Make a new material. Make a new material. We know how to do it. Make the pore size bigger, right? We know how to do that. So go ahead, try it out. We have spaces at MIT that are all about trying it out. See what happens. Thank you for that question.
Well, thank you so much for your presentation. So my question is, like, in like maybe 2 or 3 lifetimes from now, how far do you think material science can get to? Like, do you think in the future there's going to be a rock that'll tell you what disease you have just by putting a bomb on it, or I don't know, maybe like a special intelligence group that will work on any processor that you put it on? What do you think is the upper limit of this field?
Well, so there's so many ways to approach that really thoughtful question. One is to say, first of all, let's acknowledge that societies for thousands of years have been defined by materials, right? The Bronze Age, the Iron Age. Right? So what was it, by the way? Iron is so plentiful. How can it be that it took so long for the Iron Age? I mean, iron is everywhere you look in the Earth's surface. Why did it take so long for the Iron Age to develop? Nobody thought of it? Yeah.
You have to process it so it's usable in a tool.
So, exactly right. What does that mean? Process it so it's useful as a tool.
I don't know too much about iron, but I know about bronze. You need tin to make bronze.
Yeah.
But I don't know much about iron.
Okay. What about iron?
You need a higher temperature to smelt iron than
Thank you. Thank you. So indeed, indeed, iron, you will go out into your backyard with your shovel and you will find exactly 0 iron, Fe. You will find truckloads of Fe3+ or Fe2+, ionized iron. Because iron as a metal is crazy unstable. You know that because it rusts, right? That's the oxidation of iron. So you will not find iron. So the first thing that has to be done if you want to build a tool is you have to smelt the iron ore to get it down to metallic iron, and that takes temperatures that nobody knew how to make until in the history of human civilization quite recently. But then once you know how to make it, now you can build tools. And we have to acknowledge weapons, right? So that's always a part of materials development, right? Is that they will be used for horrible applications sometimes. But so one part of the answer to your question is materials have defined societies for thousands of years, but I've had people say to me, we're done with Bronze Age, Iron Age, because now we're living in a world where you already saw the lithium, lanthanum, zirconium oxide. What is that? 4 different elements. 5 different elements, 6 different elements now are routinely coming into play in the development of new materials because of AI. Right? We have the ability to tune properties to exactly what we want. We tell the computer, here's our profile, here's what we want. It has to be stable, so when you have the chance to take thermodynamics, take it. Because you need to know what material will actually be stable when you make it. By the way, I teach thermo, so we'll have you in class again for that. So all of these things come together to define what it is that's possible. Now, so where are we going to be 3 generations from now? I don't know. In some ways, things move very, very quickly. In some ways, they don't move nearly quickly enough. I can tell you, and this is the last sentence, and then I'll let Joel have it. I can tell you that the days of burning things are about over, right? We have lived, I spent my entire life thinking, you need energy, you burn something. It doesn't have to be that way. right? I'm standing here telling you about methane, and the first question is, why don't you use electrolysis to separate it? Well, the answer is, well, why don't we, right? That's the right question. Why not? And so as we develop, we haven't actually been burning things that long. It's really only a couple of hundred years. And those days are nearly over.
We're going to go online for the next question. Francesca?
Brielle, could you unmute and ask your question?
Oh, I posted it in the chat, so like just recently. So this is my question. Have you heard of Teflon, a chemical used for making frying pans non-stick, becoming a disaster for West Virginia residents due to it being a carcinogen? Like, there's a whole documentary about it online, and my class watched it during 8th grade. I found it very interesting, and considering we were having a discussion about how chemicals can be used for good, there's this other topic about like them being like causing harm.
Okay, so I didn't hear all of the question, but let me say what I think I heard, and that is, but Kirk, aren't there times that materials are used for bad? In addition to using them for good, or materials are developed that have unintended consequences, and absolutely, that happens all the time, right? And so we need to be listening to our communities as they tell us what it is that concerns them, right? And it is not the proper answer of the engineer and scientist to say, no, let me show, aren't you paying attention to how good this is? These pans are non-stick, aren't you paying attention to that? When they're saying, yeah, but people are dying over here, right? And so we owe it to the communities of which we're a part to be listening all the time as these different technologies are developed.
Esther, do we have one on that far side? I will add, Freon is another example of an excellent chemical that was stopping fires, right?
Right.
And look what the impact of Freon, right?
Right.
The testing.
Thank you. Yeah, exactly.
Hi, thank you so much for the talk. I just wanted to ask, so you mentioned LLZO as a promising solid electrolyte. I've also heard that MXenes are really good at storing energy. Why did you go for LLZO? What are the limitations of LLZO compared to MXenes and MXenes to LLZO?
So why did I choose this one? So the answer is I could have picked 100, right? One of the problems that I have in a talk like this is I sort of make it sound like there are these breakthroughs and that there are people who are going to get, I don't know, rich and famous or something. That does happen, but not very often. Really what happens is there are thousands of people working together to find solutions to problems we care about, right? And so I can't tell you the advantages of this material over that. Why did I choose that one? Because it's a nice story, right? It's a nice design problem. But there may be 56 materials that are better, in fact, at developing this, and people in the field will know them. But what we know is that we have the tools in our toolkit to kind of think through these issues. Okay?
John Galvez, do you want to unmute online?
Yeah. Hi, I'm also from Iowa. It's really cool to hear that.
Where, John? Where?
So.
Where?
Oh, sorry.
Where in Iowa?
In North Liberty, Iowa, just right next to Iowa City. Actually.
Yeah, so I'm from Pella. Have you ever been to Pella?
I have, yeah.
See? John and I, we go way back. Go on.
My main question, so you were talking about how we can use water from the earth to basically create that ammonia. And I was wondering, like, what types of concentrations would be needed for that? And could you use, like, agricultural runoff? Like, we have tons of that pollution in Iowa. Could you take that and just make it into more fertilizer?
So John, let me deal with the second part of your question, which is, aren't there ways to kind of capture some of the ammonia that already exists? Certainly, and yes, John, one of the things I like to talk about in my class is drinking water in the state of Iowa, right? And how dangerous that has become for so many residents for this reason, right, of runoff. And, but in terms of ammonia, you don't have to think very hard about ammonia, and you start to say, wait a minute, aren't we producers of ammonia? We are. And so, in fact, there is a whole technology out there for parts of the world that don't have access to ammonia-based fertilizers. Can we simply recover the ammonia that's in human waste? Right? It's there. It's the nitrogen is all. So what makes ammonia production hard? It's the nitrogen-nitrogen triple bond. That's it. It's the nitrogen-nitrogen triple bond. It is so strong that it's really hard to break that. But once it's broken, you can do lots of different things with it. Then that's what makes it available to the plants. And so is it possible to use that? And yes, but the biggest problem with relying on the human as a source of ammonia for fertilizer is they don't actually make enough. Even if you had access to the human waste of 1 billion people, you still aren't going to get enough tons of ammonia, which is what you need, in order to work this fertilizer problem. So doggone it if the numbers don't come to bite you sometimes in problems like that. Thanks, John. Back to you, Joel.
All right, let's see. I think right behind Esther, we'll ask one more question here, and then yeah.
Hi. You mentioned about how
Are you from Iowa?
Huh? No, I'm from Jersey. It's kind of weird.
Okay.
But yeah, you mentioned about how, guys, Jersey's not that weird. Like Jersey's a bit weird, not that weird. Anyway,
where in New Jersey?
Bergen County.
Yeah.
Yeah, it's pretty cool.
Yeah, it's pretty cool.
By the way, you mentioned.
And you're cool.
Oh, thank you.
Yeah.
You're even cooler.
Yeah. Thank you.
Anyways,
so why is a young man from Bergen County, New Jersey here?
Because it's fun.
Okay. So are you living? I mean, how does that work?
Well.
Are you living here? Are you?
Yeah, I'm living here. I'm living here.
Cool. All right.
Yeah.
All right. Back to you.
Okay. You mentioned about how you ask AI for like stuff like that, with like materials and finding properties. And I know like Google Gnome is a thing with, from like I think 2023.
Correct.
I forget. But how do you think AI has made research easier for material science? And a second question, I guess, is like, what material do you think was the coolest out of like your professional career? Yeah.
Oh, well, okay, so for me, the material that I think is coolest, because it's where my research was centered in my faculty days, is, you know, we have these semiconductors, and semiconductors have properties that are associated, that follow directly from the fact that they are infinite arrays of atoms in 3 dimensions, perfect arrays. So silicon, the absolute foundation of today's microelectronics. The silicon in your phones is perfect. It's perfect silicon. There's no defect. It's perfect. Well, that perfect silicon has properties that come directly from the fact that it's infinite in 3 dimensions, an infinite periodic array. Now, you might say to me, Kirk, you clearly haven't looked at an iPhone lately because it's not infinite, right? It's confined. It has edges. But remember how small atoms are. Atoms are so small that if an atom were the size of a tiny green pea, and we had 1 mole of those atoms, 6 times 10 to the 23rd, little green peas, they would cover the planet Earth and 250 other planet Earths with a 4-foot blanket of little green peas. Atoms are small, right? Atoms are extremely small. And so we think of that device as quite finite, but to the atoms, they're infinite. My research deals with, well, what happens when you make a semiconductor so small, a piece, a quantum dot, that every atom can see the edges? And if gallium phosphide is orange because of the band gap of gallium phosphide, that is because of this infinite periodic array, and I take a piece of gallium phosphide and I cut it in half so many times that it is so small that every atom can see the edge, then that piece is left to ask the question, what color am I? Right? And that answer is actually, it's all about quantum mechanics and quantum confinement, and I love that stuff. And so those are my favorite materials, but they are a part of your quantum LED TVs. So technology, so I joined the faculty 35 years ago. They're now in your living room, those quantum dots. But, and they're the same quantum dots that were doing the detection of the gastric cancer. Those are gold quantum dots. And so, fascinating stuff. We must be out of time.
Let's hear it one more time for Kirk Kolenbrander. We are actually going to be very adventurous. I'm going to ask the students from Serious Games with AI, Ishika and Yuli, to join us and unmute. We are going to do a virtual T-shirt presentation, Kirk.
Oh, wow.
Hi, my name is Ishika Shalpati, and I'm part of Serious Games with AI. First of all, thank you so much for taking the time to speak with us today. I really enjoyed your presentation. And it was super motivational to see how the decarbonization cement project just started as a student research project, but turned into so much bigger with that initiative.
Thank you.
It also made me realize that how the small projects that we're working on in BWSI can be transformed into something so much more with just hard work and perseverance.
Thank you.
And Yuli O?
Hi, my name is Yuli. I'm also from the Serious Games and AI course. I really enjoyed your presentation and learning about the materials angle to approaching problems and also ways of energy storage. And like Ishika said, Jacqueline's project that she worked on as a freshman was super amazing and motivational to see. As a small thank you, we'd like to give you a
Thank you. Thank you. Thank you.
Ishika, can we highlight Ishika and Yuli one more time, please? Can we highlight Ishika and Yuli one more time, please, so we can get a picture with them behind Kirk?
Thank you.
All right. Thank you again, Kirk. We do have a couple of quick announcements. One, we do note for the in-person program, the classes start at 9 a.m. It seems like now that we're into our second week, we don't want to start slipping the start time of the classes. So we ask you all, please be in person, be there, be present at 9 a.m. for the start of classes. For all our virtual classes, classes start at 10. We ask the same question for you to be present and attending at 10 a.m. Eastern for the start of those classes. I know that's early for some of you on the West Coast, but this is what we signed up for to do this. So please, please, please be in person. For the people commuting in next week, check the MBTA website. Part of the red line will be down. And you will need to adjust your schedules accordingly. All right. So, lastly, make sure you clean up around your seat. We don't want to leave any trash here. All right. Synthetic aperture radar. You guys you're set to leave. Over here, e-textiles, you can start out.
Yes? How are you? Good. Thank you. Thank you.
All right, autonomous underwater. I see your TAs are here.
Hi.
Thank you for giving that
Of course.
presentation.
Of course.
You talked about quantum particles.
Yeah.
So I actually had a question. So